at this piecewise piece. By the way, this is our last unit dealing with piecewise function and limits. I know the end of the year is coming up very soon. I'll show you a calendar here in a second just so you guys can get a full scope of what's left. But this is actually part of how we start the calculus next year. So if you are going on to calculus, you might start with piecewise functions and limits. So just so you guys are aware, how do we view piecewise functions? Well, it's called piecewise functions for a reason. It's a function that's made up of a collection of other functions that are restricted to intervals as a domain, your x values. So here are your restricted intervals, which means anytime I'm dealing with a number for x, an input that is less than or equal to -4, I have to use this equation. That's what the function is. And then anytime I have a number that's greater than 2, I have to use this equation to find the output. And that's the goal with piecewise functions. So if I have to find f of -10, remember, -10 is your input. That's what's going in. So then I have to look and see, well, is -10 less than -4, or is -10 greater than 2? Which piece does it fit in? Well, -10 is definitely less than -4. So I'm going to have to use the yellow equation. And you could do all of this in your head. But what I need to do is I need to take that equation, 1/2 x plus 7, and evaluate that piece at -10. So then I would do that algebra in my head. Half of -10 is -5. -5 plus 7 is -2. So then we would go to 3. Now we have a new input. This is kind of like saying x is equal to 3. Well, is 3 less than -4 or greater than 2? And right there, 3 is greater than 2, so I'm going to use a new function or a new piece to evaluate the 3. I'm going to take negative of x minus 3 and square it. But now we're plugging in 3 for the second piece equation. And then we just have to follow proper order of operations. This says take, well, 3 minus 3 is 0. 0 squared, and the opposite of 0 is 0. And then we get to f equals, or f of -4. Well, the reason why we can do this for this one right here is because of the equal to sign. If I didn't have that equal to sign, I wouldn't be able to solve this part. But -4 is less than or equal to 4, so, or -4. So I'm going to plug in -4 into that first piece and simplify. Half of -4 is -2. -2 plus 7 is a positive 5. All right. So then we look at a couple other things. What if we, and this is getting towards what we're going towards in the next couple days, is what if I'm just past -4 to the left of it? So -4.1. Well, -4.1 is still less than -4. I'm going to do that same work. Plug in -4.1. If I cut that in half, that's -2.05 plus 7. And let's see, is that 4.95? And if I keep with my highlighting theme, that's going to be for the yellow piece. And then I've got 1.9. Well, let's think about that. If I put 1.9 here, 1.9 is not less than -4. And if I put 1.9 here, 1.9 is not greater than 2. So what does that mean? For this function, and we're going to write this a lot. So DNE stands for does not exist. can't solve that because it does not fit within the range of the domain that's given. And sometimes, as we're going to look at the graphs of these today, sometimes you have complete gaps in your graph. It's not always connected. And this would be an example of a non-continuous function. And then same thing here, what about 0? Well, 0 is not less than 4, and 0 is not greater than 2. So we actually have two different cases where our functions cannot exist because they do not fit within the accurate domain. All right. So, any questions on that? Yes, sir. Oh, it should. I knew I was going to make at least one mistake. Let's see, negative 1/2 times 10 is 85. That should be a positive 2. Good catch. Thank you, Michael. Anything else that I missed? Okay, so that just is how we evaluate piecewise functions, but what I really hope you think of is if I asked you to graph this, our graph is going to have two pieces. Why does it have two pieces? Because there's two different equations, and each equation is going to be over a specific domain, which remember, domain is your set of x values. All right, so we are starting, let me see if I can put this up here. We're starting what we're going to call 12.0. And the reason why it's 12 is if we haven't been using the textbook this year, but there's not 12 chapters in our textbook, I believe. And the last thing we do is this idea of limits. And our goal with this last unit is to really help prepare you guys so when you walk into calculus next year, at any level, you have an idea of piecewise functions and this idea of limits. So I just want to show you this. The details aren't super important for you to remember, but here's where we're at. We're going to do limits. No, I forgot to grab the week before that. Let me just pull this up. This will be better. So here's where we're at. Today is May 4th, 5th, 4th. We've got piecewise functions, and then we're going to do more piecewise functions on Thursday. Then we have a quiz. And then May 10th, we're going to do something called limits with a quiz. And then we've got more limits, but a different way to look at them, and a quiz. And then we have a review and our final. Our final is just going to be on this last 3 weeks of material. So piecewise functions and a whole bunch of stuff on limits. I think you guys are really going to like limits if you're paying attention and you've done the homework, because it's pretty friendly. But what does that mean for seniors? What does that mean for juniors? I can't access my scroll. Maybe I can. There we go. So our final is going to be on the Thursday. I think it's like the 27th of May. And seniors' last day is that Friday, officially. So what we would do is we're going to take the final. Everybody will take the final. And then seniors, you're really going to have basically a day to do a remediation. So you'll get your grade and the final. And then you'll have to do your remediation if you choose to. And then you're done. Juniors, I will see you back in school on the next following Wednesday, or Tuesday, I believe. So juniors, we don't have much to do this week, but you are expected to show up for attendance. That goes for people on Zoom as well. We might just have a quick little survey of how did the year go. I might share with you a little more detail on what to expect for calculus the following year if you're moving on to calculus. So I just wanted to show you that so you guys have an idea that, man, we don't have a lot. If you count this week as a full week, 1, 2, 3 full weeks of learning, and then we've got this week here, which is a full week, but it's really review and final, and then a nice relaxing end into June. So some of us need to really make a push to get missing tests, quizzes, homework, all that stuff in. My grade book will be closing on the day that you guys take the final here. Just so you guys are aware, because I'm not going to be, I have a lot to do to get prepped and ready for end of the year grades, and I don't want to be going back this week looking for all your missing assignments and grading a whole bunch of stuff. So I'll let you know as we get closer to it, but just, you can think of that as the 27th of May, the grade book is going to close officially. All right, so we don't need that. Our goal today then is to really look at piecewise functions to be able to both write and graph. And it could be a challenge because what I've found is students aren't awesome with this whole idea of graphing and domains. And that's what today's all about. Before we do that, I know this isn't something that's going to be super challenging, I think, but I do want you to keep in mind, given a piecewise function, when we start getting into limits next week, don't forget how to read a graph and find a point. So what I'd like you to do is, you don't have to draw this graph, and maybe just somewhere on your paper, put down the answers here. And I want you to find f of 0 based off of the given function, find f of -3, and then the bottom one is a little bit of a review / challenge. Do you remember how to do f of 1? So we'll give you a couple minutes to work on that. So f of 0, remember, this is your input and output. What is the output when x is 0? Down 1, 2, 3, 4. So -4. What about when x is -3? So go over -3. Now here we have the idea. This is where -3 is. We're looking for the filled in circle. So that is the same as f of 0. So remember, the open circle means that every point up to it is counted, but not the point itself. And then the filled in circle, that's the one that shows the actual value at that point. So what if I have x is -6? So 1, 2, 3, 4, 5, 6. Here's -6. I need to go down until I hit this output, which is 1, 2, 3, 4, 5, 6, 7. So that's the spot, -6, -7. And then f of 1. So when x is 1, we run into that same issue. I have an open circle, and then I have a closed circle. The closed circle is the location, and that's the actual point at -1. And then we tried to trick you a little bit here, and we threw the composition of a function in, which, remember how we approach that. We always deal with the inside function first. So I need to find f of 1. Wait a minute, didn't I just do that? So I know what f of 1 is. F of 1 is -1. And that'll take care of the inner part, but then I still have the outer f. So then we have to take the answer from the inside, and now that's my new x value. So now I have to go figure out what is f of -1. I'm going to go over -1 and see that it is right on that line as well. And I'll get -4. That's called a composition of a function. When you have a function inside of a function, you might remember that. Another way to write that is f of -1. You ever seen that? F of f, or a lot of times it's like g of f, or g of h of f, or g of h of x. All right, right, one last thing. This is just a little bit extra, but remember, all of these are locations, right? They're all points. The way it's written right now, f of 0 equals -4, that's function notation. It's the exact same thing as writing it as an ordered pair, 0, -4. So that's really important for us just to remember. Every ordered pair can be written in function notation, or it can be written in the coordinate pairs, x, y. All right, so you'll see next week why this slide was important. And I'll tell you what, my calculus kids often get these problems wrong. It sounds silly to say, but it's because of how we learn limits. So this is just a point. It doesn't have anything to do with the limit side. All right, we are going to do some graphing here. If you don't have graph paper, I have some here. Those of you that at home, you'll have to just make a graph if you don't have your own graph paper. And so those of you at home, I know you guys don't have the luxury of having a smartboard or graph paper, so here's what you can do at home. We're not going to be super accurate. It will help. But if you're at home right now, do your best to evenly draw about 10 tick marks in each direction. And you can see I'm not even doing a great job here. But go 10 in each direction if you could. And then same thing up above. Go 10 up above. We're not going to do a ton of graphing here, so you'll manage just fine if you don't have graph paper. So if I tell you to graph, before we put our pen or pencil to paper, how many pieces does this graph have? 2. Right? Look at the equation. There's 2 different equations for 2 different domains. So here's what I'm going to do, is we're going to start off with just the first one. And what I would do if I were you is use a different color if you could, just to help you out with your notes. So I'm going to graph this one. Anytime x is less than -1. Now you clearly do not have to do all of this work, because you could probably do it in your head. But I need to get points. I need to take that equation, I need to get points, and then I can plot them on the graph. And I'm going to start at -1. And my table, it's not going to follow perfect order, because I'm going to go -1, -2, -3, -4. And then you might notice a pattern. You probably could graph this without even making a table. Well, let's just evaluate each one of these points. Now, I'll tell you this in a second, but let's plug in -1. The -1 is going to go in for x. I'll get negative of -1 minus 2. Just be careful there. The negative of -1, or opposite of -1, is positive 1 minus 2, which gives me negative. All right. Now, if I go to my graph and plot that, if I go over 1, down 1, what am I going to put right there? An open circle. All right? It's an open circle because there is no line saying it's equal to. Now you might be able to go right from here and say, wait a minute, isn't this graph just a linear graph? Remember y equals mx plus b? What's the slope on this graph? -1. I'm going to go down 1 over 1, down 1 over 1, and you can totally do that. If you don't see that connection, then let's go ahead and take -2. And let's plug -2 in. Opposite of -2 is +2. -2 is equal to 0. And then same thing here. What if I plug in -3? I get opposite of -3 is 3. 3 minus 2 is 1. And here's where you can see the down 1 over 1 slope. Right? You can keep plotting that. However, I don't like the way this is going. What am I doing? Yeah, what am I? Okay. Go over 0. Go over -2 up 0. Go over -3 up 1. There we go. I don't know what I was doing there. And then same thing. Keep graphing, and you're going to just plot those points. But hopefully you notice the pattern. Go over -4 up 2. Your slope is 1. It's -1, so I'm going to go down 1 over 1, down 1 over 1, but I'm going to follow that pattern in the other direction. So you could just keep plotting all of those points without really generating a table. Okay? But we know for sure we can't go past x equals -1. Okay? That's my domain. It says this part of the graph is only true for numbers less than -1. Now, I'm just going to shrink this, push it off to the side. Now we have to basically do the same thing for 5, because this is saying x is greater than 5. Well, right away, even before we start graphing, you should think there's going to be a big gap, because I am not accounting for the number between -1 and 5 on this graph. So none of those points are going to exist. But now let's do a new table for numbers greater than 5. So 5, 6, 7, 8, 9, and so on. Some people even circle this. Why might I circle 5 right there? That's the point, right? We don't want that point because it's not an equal to, so maybe I could have circled this one as well, because we have 2 open circles for each one of those. But I still need to know its location. So we're going to plug in 5 for x. And you could do that in your head, right? 30 minus 2 tells me go over 5. 1, 2, 3, 4, 5. All right. And down 2. Oops. And I almost screwed up. What did I do? I put a filled-in circle. It's not supposed to do that, right? You go over 1, 2, 3, 4, 5. Go down 2. That should be an open circle there. I do that all the time, and I end up erasing. I catch it. I have like a check and balance in my head. Now again, if you realize the slope here is 6 over 1, and you know one of the points, you can go up 6 over 1, up 6 over 1, and keep going. But here we got 30. Excuse me. Okay. 36 minus 32 is 4. I'm going to go over 6, up 1, 2, 3, 4. And then the next point, you know, is going to be up 1, 2, 3, 4, 5, 6 over 1. And you can use that idea of slope. You don't have to keep generating a table. The table's there just to always give you a backup. If you don't remember our patterns for linear equations, or even the patterns when we have quadratics, make a table. There's no harm in doing a little extra work. Okay, it's that 42 minus 32 is 10. I think this should actually be right here. 1, 2, 3, 4, 5, 6. So there you go. There's my two pieces to my graph. And notice, they're not connected. There aren't pieces for -1 through -5. So if I ask you to evaluate, what is f of -1? Notice it's an open circle. So that doesn't exist because that circle is not filled in. If it was filled in, then our answer would exist. But it doesn't. So I could ask you something like this. What's f of 0? Well, when x is 0, there isn't any graph or any part that crosses it. So that does not exist as well. So that's the idea of those points. You really have to make a connection to that. Now, I will mention that not every single part of the graph is going to be linear. Okay? Some of it could be a constant. Some of it could be a parabola. Could be some weird function you've never seen before. I'm going to actually add one extra, you don't have to write this, but I'm going to just add one extra step to this and just see how you would interpret this. What if I put a new piece here and I said that f of x is equal to 5 for any value between -1 and 5. Think to yourself right now, if I added that green part in here, what would that look like on my graph? If you can't get it, think about what the table might look like as well. So maybe you got it already. Or maybe you're thinking, you know what, I'm not sure. I'm going to make a table for values between -1 and 5. So -1, 0, 1, 2, 3, 4, 5. So when x is -1, what's the output? 5. There is no x, which means the answer is always 5. For all those values from -1 to 5. So when x is 0, it's 5. When x is 1, it's 5, 2 is 5, 3 is 5, 4 is 5, 5 is 5. Well, what does that look like as a graph? If I plotted all those points, what am I actually drawing? Straight line, a horizontal line, right? So when I go over -1, I'm going to go up 1, 2, 3, 4, 5. What am I going to do right here? It's a closed circle, right? Because now we have the closed circle. And then when x is 0, it's still 5. When x is 1, it's 5. When x is 2, it's 5, 3, 4, 5. And there's just an extra piece. Now, every single x value you could ever imagine is represented. So now, this would change it to when x is negative 1, my output is 5. When x is 0, my output is 5. So that's just things you have to be aware of, is sometimes if it's just a number, 5, that's a horizontal line for every x value in its domain. Okay, now let's have some fun. What about the absolute value of x? You may remember what that graph looks like from Algebra 1. And we're going to have even more fun. No, it's going to get too big. I can't. I was going to change it to x squared minus 3, but that would be off of our graph, and I'll just leave it. So as you're setting this up, we have two pieces, right? So we know I'm going to have two different types of graphs. Now, sometimes they can be connected, sometimes they're separate. We don't know until we finish graphing them. But the yellow piece is an absolute value function. What shape does an absolute value function make? The V. Right? So we might not get the full V. We might not even get the bottom part of the V. But this graph, if I was to graph it over its entire domain, would look like that. But what if I only have part of it? So it could, if I only take a little part of it, if I take this part of the graph, it looks like it's linear still, right? But it overall is still from the absolute value. That's why I'm a fan of making a table if you're not super familiar with that function. And some people even like to write the equation. Well, what is the y value? It's the absolute value. And I need to do it from negative 7 all the way to 4. And again, the tables are just there to help you. If you can do this in your head, you don't need to plot the table. And then remember, well, what happens if I plug in negative 7? The absolute value of negative 7 is positive 7. Right? It just turns everything positive. Which means, do I really have to show the work? Do I have to show that the absolute value of negative 6 is positive? No. You know that every value is going to turn positive. 0 is going to stay 0. The absolute value of 1 is positive 1. 2, 3, 4. So you could generate that table very quickly, and then you can plot those points very quickly as well. If I go over 7, I have to go up 7. And you might even know the pattern of the absolute values, so you could just follow that pattern down. Okay? If not, go over negative 6, up 6, up 5, up 4, 3, 2, 1, 0. And then we're going 1, 2, 3, 4. Now I did this without asking, but what should be right here at negative 7? Open and close. Close, right? Closed circles for both of those because of the line underneath it. And that means closed circle at negative 4. And you just have your second piece. If you want to make your table, you can. Or, what's the slope here? Which, by the way, this is linear. What's the slope on that problem? 1. So if I can find one point where it's going to start, let's do 5 minus 3, which tells me my one starting spot is over 5 up 2, and that's also going to have a closed circle. Then I know its slope is 1, so why generate the table? I can go up 1 over 1, up 1 over 1, and I'm going to go all the way to 9. So 5, 6, 9. You do have to be careful, because if you drew arrows saying this linear line went forever or this one went forever, it's technically wrong. You have to follow the domain. And for the red one, it tells us to start at 5 and end at 9. You know, I'll show you one last thing. I don't know if you want to look at this. This could get you in some trouble. But if I asked you to graph this linear piece, remember the y-intercept is negative 3. So I'd go down 3 right here. Don't draw this part here. And then the slope is 1. Up 1 over 1, up 1 over 1, up 1 over 1. And you just keep going. Well, you could just start there and graph, but not record any of these points until you get to 5. And that way you don't even need to think about a table. You're doing y equals mx plus b. The problem is if you leave those marks there, it's technically wrong. And that's the danger, is sometimes kids get so used to doing it. Here's the issue with leaving this. And again, I'm going to erase this, so don't draw this. But what if I accidentally did that? And I said, I'll start here, then I had these points. Here's the issue with this. If I had the blue, the green, and red, if I had all this as a graph, and I told you to tell me what is f of 2 right now. What is f of 2? Well, f of 2 is right here. But isn't it also right here? We can't have that. That is the definition of a function going all the way back to Algebra 1, is every single input has to have one specific output. So when x is 2, it always has to have the same output. It can't have an output of negative 1 and 2, which is why you have to be very careful not to add any extra pieces to your graph, because there's something called the vertical line test, which you might remember. So anyway, that's just a little extra piece there. Okay, now I would like you guys to take this graph and write the piecewise equation for it. And try to get this. So here's the graph. And I shouldn't even have given you guys this, because we should know there's 2 pieces to the graph. So let's give that a shot, and then we'll go over it in just a second. So what I like to do first is deal with the domain. I like to fill in the first piece, let's do this one in red. So I know it's a filled-in circle, and where does it start? It starts at -2, and then it goes all the way. It's just going to keep going. It's going to go all the way to -infinity. So the way we do that is to say, you know what, this is going to be true for any value when x is less than -2. However, closed circle. Right? So the closed circle, you have to put the line underneath it. And then I just have to find the equation for that. Well, this is a linear equation. A quick way to do it is y equals mx plus b. And you can follow this pattern up using rise over run. So if I look here, if I go from one point to the next, I went up 1, 2, 3 over 1. Up 1, 2, 3 over 1. 1, 2, 3 over 1. See how if this was continued, it would hit that y-intercept. So what do I have? I have a slope of 3 and a y-intercept of 10. So that would be 3x plus 10. So that's one way to do it. Now, that's not always the best, because what happens if I can't see my graph here and I don't know it's going to hit that y-intercept? The other way to do it is this, and this is going back to Algebra 1. Remember point slope? I need a point, any point on that function. So maybe I use this point at the spot -2, 4. Right. Now remember, that's the y1, x1. Officially, it's subtraction of the negative. So that's x1, y1. And then we just saw what was my slope. Well, from one point to the next, I went up 3 over 1. Well, we know my slope is 3. And then if you algebraically solve that, distribute to 3. Remember, this will be a plus. So 2 times 3 is 6. And if I add 4, it's the exact same thing. So there's two different ways to do it. I would recommend using your graph because that's probably the fastest, but it's not always guaranteed to work. So then I have the second piece. Open circle, my equation's going up. Well, where do we start? We start at 4, and then x is getting bigger, so x is going to be greater than every number past 4. Now notice it's an open circle, so I don't put a line underneath it. Now here you could use that same idea of slope. If I go up 2 over 1, my rise over run tells me I've got a slope of 2. So you could follow that pattern down. So go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. See your y-intercept right there? So this would be a 2x plus -7, or you could just write 2x minus 7. Okay. If you don't like that, then you would do the point slope. Which, by the way, this equation is used probably you'll use that 1,000 times in calculus. So it's not a bad thing to focus on it. So what would I do? I'd pick the point here, 4, 1 as x1, y1. So 1, 4. I know my slope was positive 2. And then if you distribute and solve, you should get the same thing we just had. Two different ways of finding that. Nice review of Algebra 1 there. Okay. Be very careful with your domain. That's definitely something that students make errors on. So I want to show you delta math quick because there's one. Let me just show you the assignment here. So first piece, really quick. Name a point. What is f of 0? Right? So find 0. That's super quick. Find f of 0, but now you're picking which piece of the equation would 0 belong to. So that's nothing tricky. Here's where it gets a little tricky. All right? It says graph the following function on the axes provided. So I have to graph this. So I want x plus 5 for this piece. So what do we have to do? We have to drag to make the line, click the line to delete it, and then click on the endpoint to change it. So I want x plus 5. What I'm going to do is go up to plus 5, and I'm going to do a slope of up 1 over 1, up 1 over 1, up 1 over 1. And I'm going to go for as much as I need to. Now, this is for x is less than negative 2. So I'm going to take this pattern, and hopefully it'll let me extend it. My angle is kind of weird. Is that a straight line right there? Yeah. Okay. So now notice, I want this to keep going forever, but I need to make sure that it actually doesn't start until 2. So if I make a mistake, like I did, I didn't make it, I needed that, I'm going to just move this and see if it'll let me start at negative 2. Oh. This is a really weird angle for me. I might have to delete that over. Okay, so I think what I'll do is start here, and then go down 1 over 1. And then you're going to go for the rest of your graph. Okay, but notice how that's an open circle here. So then you click on that to make it an open circle. And then for 4, when x is greater than 1, my output is 4. Now notice, that's a number, right? So every output is going to be 4. And then this will have an open circle. I wish they had arrows. Maybe, no. Is that an arrow? Yeah. There we go. So, assuming that I graphed this one right, gave me the answer. Okay. Then there's this piece, which is, this is the spot that I think could be really tricky. We have the absolute value minus 2. Well, what you have to do for that is I want to take this, I know this is a v, so I'm going to graph that, but remember what the minus 2 does? That's a vertical shift down. So you grab the vertex, this blue dot, and you shift it down 2 units, and then it says click done. So I have it in its right position, however, it's not set up from negative 7 to 1. So I'm going to grab this arrow. I'm going to go from negative 7. Is that on? I'm at a really bad angle. Does that look good? I think that's good. And then I got to bring this to 1. Now we do have to be careful. Notice they're both closed circles. So I do have closed circles. So that part is good. Now I have to select the bottom piece. Well, what is that? That's linear with a positive slope. So that's going to give me a straight line. The minus 8 is the y-intercept, so I got to just drag this down to a minus 8. And then I've got from 2 to 5. So now that I have the line in the right spot, I'll click done. And then I'm going to scroll this over until it starts at 2. And then I have to make sure it ends at 5. All right. Now, notice, what type of circles should they both have? Open. So then you just have to make sure you click on it. And if you click start over, I believe that starts just that graph over. But then it's finished. It locks it into place. Let's see if I did that right. Yay. And then it walks you through to see the answer. It basically, step 1, you graph the absolute value. So it gives you some feedback there on how to do it. I just see that as being a little bit of a challenge. And then this one is just write the equation, which is kind of friendly. So anyways, I wanted to show you that just because I could see some potential questions. This part is on our video, so if you do get stuck, you can go back and watch maybe the last 5 minutes of the video, and you'll get some feedback on how to do those. All right, that's all I got. Enjoy Delta Math homework tonight. Adios. Have a good day.